We are from Group 7. We're present about the slope stability. Our group members, first one is Muhammad Faiz, CF220017, and second one is myself, Darren, CF220024, and the third one is Muhammad Haziz Sikri, AF220091, and the last one is Pami Daniel, AF220073.
Slope failure, whether caused by natural events or human activities, significantly impact people, the economy, and the environment. It occurs when the force on a slope exceeds the soil strength, leading to instability. Geotechnical engineers assess slope stability by examining factors like geology, drainage, groundwater, and soil shear strength, despite challenge posed by soil diversity and data collection limitation. They use the factor of safety (FOS), the ratio of resisting to driving force, for assessment. Slope failures can result from various factors including gravitational force, water seepage, surface erosion, sudden water level change, and earthquakes. Water is crucial in triggering landslide by saturating soil and reducing cohesion, while human activities like logging reduce soil stability. Dynamic force from events like earthquake, blasting, and volcanic eruption weaken soil strength, causing failures. Seismic events can lead to dynamic liquefaction, causing soil to behave like fluid, and undrained conditions during earthquake can lead to rapid failure. Reservoirs with rapid drawdown are particularly vulnerable due to sudden loss of water force and undispersed pore pressure, potentially leading to collapse.
For the application, the process that involves analyzing soil failure is a comprehensive approach that integrates field investigation, laboratory testing, risk assessment to assess and mitigate potential hazards associated with soil instability. The first step in analyzing soil failure is conducting a thorough site investigation. This entails gathering data on soil composition, geological information, surface topography, and hydrological condition. Field surveys and geological mapping provide valuable insight into the characteristic of the site and identity potential factors contributing to soil instability. Laboratory testing is essential for evaluating physical and mechanical properties of soil sample collected from the site. Various tests are performed, such as standard penetration tests, cone penetration tests, and pressure meter tests are commonly used for method to measure soil resistance and deformation characteristics. Furthermore, risk assessment plays a crucial role in analyzing soil failure by evaluating the likelihood and consequences of potential failure. By quantifying the risk associated with soil instability, engineers can prioritize mitigation measures and allocate resources effectively to minimize potential hazard. Last but not least, mitigation measures for soil failure may include stabilization techniques such as soil reinforcement, drainage improvement, vegetation control, or structural intervention.
The case study that I chose is about the failure of the Cathedral of Notre Sicily, the Saint Nicholas Cathedral for dynamic characteristics from the soil from in situ and laboratory tests. This focus on the dynamic by the post-seismic structure collapsed on 30 March 1996. From this case study, the site investigation was performed within the area 3,200 meters square, 40 meter time by 8 meter, and reached a medium depth of 81 meter. The Pliocene natural deposit mainly concerned a medium step and normal consolidated clay sand. The value of the moist content at the range from between 15 to 37%. The characteristic value for the Octoberry limit are W1 30 to 58% and WP is 70 to 22% with a plasticity index of Pi 50 to 40%. These data indicate a low degree of homogeneity with a depth of deposit by analyzing the number of flow from standard penetration test (STP) performed. There are two pictures is represent of the result for the laboratory test. The first one is index properties for native soil and the second one is a standard penetration test result. From this data, we'll be able to understand the specimen where it is isotropically reconsolidated to estimate the in situ mean effective stress. The same specimen was subjected to CLTST followed by RCT after a 24 hours rest period with an open drainage. The cylindrical specimen had a radius of 25 millimeters and a height of 100 millimeters. Okay, this is the result for the test condition for the natal soil specimen that we get from the index properties of natal soil. And the second one is the graph of a G curve from CLTST and RTC test. As you can see, the result for both of them is decreasing. This graph is represent to the damping radius curve from CLTST and RCT test. A comparison between the damping radius value obtained from RCT and CST that we get is first the volume of D that we get from CLTST is a very smaller string and it is equal to 1%. Meanwhile, the value of D that we obtain from RCT is a greatest strength interval. This graph is represent to the GO from laboratory test and different in prior condition. As you can see, the data that been used to plot this graph is STO and GTO 1978. Second one is Yoshida and Monotori 1988 for fine sand. Third one is Yoshida and Motonori 1988 Anis soil. Third one is Jamiokoski it at this is the formula for the penetration test and the laboratory test. The first one is Otoha and Gota 1978. The second one is Yoshida and Motonori 1988 and the last one is Jamiokoski 1995. Among the three methods that have been given, the method by Jamiokoski was applied consider giving a profit of the void radius and KO. In the case of laboratory tests, the GO value at the shear strength level is below to 0.001%. The proposed empirical correlation show the reasonable agreement with a laboratory result for the initial modulus value. Equation number 4 from the Jamikowski provide the most accurate thread of a GO with a dip. The accuracy is evident with a comprising GO from the laboratory test and the various of empirical correlation.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Faiz bin Ahmad Faris. The numeric card is CF220017. So, for my part is the case study at the nearest Ting Chuang Road landslide in 1997 comprised a series of three progressive larger figure on 7 July, 17 July, and 3 August. Following in history of instability in the area dating back. Okay, for that place, the major landslide during the road widening lead to remedial measure, including slope cutting and ranking drain installation. Further, trimming under the landslip preventive measure (LPM) program between 1990 and 1992 aim to enhance stability, but might have comprised the FOS factor of safety. A minor failure in 1993 preceded the 1997 event. the geology featured basalt that action as a aquatype, impeding groundwater flow and contributing elevated groundwater level, especially following blockage of natural drainage system post the initial landslide on 7 July 1997. The compound effort of the upstream recharge and upsoil drain blockage culminated in the most significant third landslide. Emergency stabilization by adding basalt plus at the toe reflected an intuitive response to counteract the reduced load stability from toe white removal. Detailed information is available in Geo report. Okay, next, site investigation. For this report also present the result preceding recent landslide event focusing on rainfall pattern and soil strength parameter. The data include maximum rolling rainfall, measure at geo rain gauge number K06 and soil strength laboratory test result from previous investigation. Maximum rolling rainfall analysis is the objective. Analyze the maximum rolling rainfall, its impact on landslide occurrence on 7 July 1997, 17 July 1997, and 3 August 1997. The table provided summarizes the maximum rolling rainfall for various durations preceding each landslide, even the corresponding estimate return period. On 7 July 1997, the maximum rolling rainfall for 31 days is 1,557.5 mm with an estimated return period of 498. Notable duration with significant rainfall, including 2 hours in 162.5 mm, 1 day 431.5 mm, and 7 days 673 mm. The rainfall preceding this event is significantly high over short and long duration, indicating instant and prolonged precipitation. On 17 July 1997, the maximum rolling rainfall for 31 days is 1,212.5 mm, with estimate return period of 52 years. Key duration with high rainfall, including 2 years, is 162 mm, 1 day 430.31.5 mm, and 15 days in 870 mm. Similar to 7 July event, instant rainfall over extended period contribute to the landslide. On 3 August 1987, the maximum rolling rainfall for 31 days is 881.5 mm, with an estimated return period of 5 years. Significant duration, including 2 hours, is 68.5 mm, 1 day in 199 mm, and 15 days 484.5 mm. This event has a comparatively lower rainfall intensity correlating with a shorter return period and potentially less severe impact. The data indicate that prolonged and intense rainfall over varying duration significantly contribute to the landslide event. The high estimate return period for the July event suggests these are rare and severe rainfall occurrence. Okay, for the next, soil strength parameter. The objective is from previous laboratory tests and evaluate their implication for landslide susceptibility. The table summarizes soil strength parameter for different soil types, comparing results from Geo 1982 and Geo 1988 investigation. For residual soil, Geo 1988 result indicate a cohesion of 2 kPa and kilopascal and internal friction angle of 37 degree. No data is available. Number of data is available for Geo 1982. For complete decomposed granite CDG, Geo 1988 results show a cohesion of 9 kilopascal and internal friction angle of 39 degree. Number of data is available for Geo 1982. For highly decomposed granite SDG, Geo 1982 result indicate a cohesion 12 kilopascal kPa, and internal friction angle is 37.5 degree, while Geo 1988 results show improved parameter with a cohesion of 15 kilopascal kPa and internal friction angle of 39 degree. For the complete decomposed applied Geo 98 results show cohesion of 7.2 kilopascal kPa and internal friction angle of 40 degrees. Number of data is available for Geo 1982. For completely decomposed diorite flooded Geo 1982 result indicate a cohesion of 2 kilopascal kPa and an internal friction angle of 28 degree, while Geo 1988 results show reduced cohesion, 10 kilopascal kPa, and improved internal friction angle 40 degrees. Soil parameter vary significantly between soil type and investigation period. The data suggests that HDG and CDG have relative higher stability, where residue soil and decomposed diorite, especially when flooded, present lower cohesion, potentially increasing landslide susceptibility. For recommendation to mitigate potential landslide, it is recommended to implement real-time monitoring of rainfall and soil moisture level. Consider soil stabilization techniques such as grouting, retaining structure, proper drainage system to enhance slope stability, and conduct periodic soil strength tests and geologic surveyor to update and refine the understanding of soil behavior under varying climatic conditions. This site investigation highlight the critical role of instant rainfall and soil strength parameter in landslide occurrence. Understanding this factor is essential for developing effective mitigation and prevention strategy to protect infrastructure and life in landslide prone area. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Fahmi Daniel, and the case study that I've chosen is the incident occurred in Japan, which is the case study number 3. Frequent incidents in Japan of soil slope failures occurred due to snowmelt and heavy rainfall in Japan. There is one incident that occurred in the expressway in Hokkaido, which is 9 years ago, and we need to understand two tests involved to understand the slope behavior, which are the permeability test and slope stability. The three pictures shown above is three different types of tests, which are conducted from the permeability test. Three different types of constant head are used, which give us the three different type of result and three average data. From the three average data, we can conclude a new average of data. The second test for the slope stability analysis is shown below. And the method we use to calculate the data is the method of slices. As you can see the data shown, there are 10 segments of slices. Therefore, we have 10 data. And by doing this test, we can understand the strength of the soil, and we can assume the line of failure for the slope. Therefore, we can assume the probability of failure before we conduct any structure along the slope. And we can also avoid any casualties or unintentional expense. And through all these two tests from the case study, I can understand that the lab testing is crucial for every soil-related problem and must be undergo every mandatory testing and the applicable result for approval to build any building on the ground. To change this theory, we must also understand every behavior of the soil to avoid any unnecessary cost and energy loss. Therefore, these two testing are very crucial for before we undergo any structure related building. The data shown below is the data taken from the lab manual. This is the data for conducting a permeability test. The permeability test is used to understand the water molecule movement in the soil. Therefore, we can also understand the size of constant head could affect the flow rate of this water. For example, such as bigger size of constant head doesn't mean faster flow rate, and smaller size of the constant head doesn't mean slower flow rate. The permeability test is also It's also crucial to conduct because we can understand the overall behavior of the soil in contact with water.
Assalamualaikum, my name is Muhammad Aziz Zikri. The case study that I've chosen is the research about study to carry out slope stability evaluation of the Jika Gali landslide in Pakistan using GeoStudio. Using two tests that will be more understandable about the behavior of the soil, two tests were conducted, which is the first is unconfined compression test and second is triaxial test, and more focusing about the unconsolidated undrained triaxial test. The slided material has 1% gravel size particle, coarser than 4.75 mm, 21% sand size particle, finer than 4.75 mm, and coarser than 0.075 mm, while the remaining 78% are fines, which is finer than 0.075 mm, out of which 35% are clay size particle, which is finer than 0.005 mm, and 43% are silt size particle. The soil has liquid limit of 38% and plasticity index of 15% according to the consistency limits measure. According to the Unified Soil Classification System USCS, the soil is categorized as lean clay with sand, and it is classified as A6 with group index 6 by ASHTO. The sample was subjected to standard proto and modified proto tests in accordance with ASTM D698 and D1557, yielding maximum dry unit weights of 18.14 kN per meter square and 20.31 kN per meter square. For the sample respectively, the in situ dry unit weight of soil as measured by the block sample is 18.63 kN per meter square. For the graph of particle size analysis of sliding material, which is this result consists of cycle and engineering properties were evaluated using classification test, standard proto and modified proto test. For the shear strength of soil matrix, we use formula to calculate the shear strength of soil matrix, which is this is the formula, and then unconfined compression tests were performed on remote samples for the determination of the deformation modulus E50, and the deformation modulus was calculated by using the axial stress versus axial strain relationship. For the slope stability analysis were performed by adopting the limit equilibrium approach in slope software based on the determined shear strength parameters along the most likely failure planes. Slope allows a variety of methods to determine the safety factor, but in this research the Morgan's price method was used due to simple geometry of the Jika Gali landslide and its popularity among the different researchers. In this method, to find out the coefficient of reliability, the slippered mass is divided into a number of slices. Then in each slice, interpart force and internal force are obtained. The Morgenstern price method considers two reliability coefficient. One is based on the result of force equilibrium in the horizontal direction, and the second is based on the moment equilibrium. So these 5 types of formula is important to obtain the data for slope stability analysis. Lastly, for the result, we have 3 types of result for the case study that I choose. The first is result of the triaxial compression test. The second is result of unconfined compression test, and lastly is the additional for result Jika Gali slope stability analysis. For the summary, the main objective of the research was to look into the impact of saturation on the shear strength parameters of Jika Gali and to assess the slope stability. This investigation includes a detailed program of triaxial compression tests by changing the cycle parameters of dry density and saturation. After this, by using this parameter, slope stability analysis was performed in GeoStudio for the determination of the factor of safety. In order to increase the factor of safety of the slope, alternation in the slope geometry was done. The following conclusion are summarized. The first is based on the triaxial compression test result. It can be concluded that the undrained shear strength of the remote samples at the particular degree of saturation increased by about 7% until 10% with the increased dry unit weight. However, the cohesion decreased about 51% as the degree of saturation increased from 35% to 95%. The friction angle improved approximately with the increase in the dry unit weight at the specific degree of saturation. Although the friction angle is reduced by about 41% as the degree saturation is increased from 35% to 95%. According to slope stability study conducted on GeoStudio, the landslide along the Jikagali road were caused by a reduction in the shear strength of the slide material due to a rise saturation level. Consequently, with the increase in saturation level, the effective normal stress decreased along the slip surface. Stability analysis of the landslide show that the factor of safety reduced as the saturation increased from 35% to 95%. When the saturation was about 85% to 95%, the slope was in the critical condition because of the low factor of safety.
For the conclusion, conducting a true examination of soil failure and slope stability involves a holistic approach, including detailed on-site investigation, comprehensive laboratory and field tests, and meticulous risk assessment. Geotechnical engineers play a vital role in assessing slope stability, taking into account factors such as geology, surface drainage, groundwater, soil shear strength. Nevertheless, challenges arise due to the wide variety of soil and limitation in data collection method. Soil stability assessment relies on simplified assumptions, and the factor of safety are crucial indicator for evaluating slope stability. By examining the force and acting on slope and soil strength, engineer can assess the potential for failure and devise strategy to minimize associated risk. The case study conducted on soil dynamite at Saint Nicola Cathedral, the evaluation of at the Jika Gali landslide and Chingchua Road landslide and slope failure in Hokkaido vividly demonstrate the significance of true investigation and target effort to reduce risk. In understanding soil behavior under varying conditions and implementing sustainable stabilizing technique can prevent slope failure that their adverse impact. Laboratory and field tests include the standard penetration test (SPT), cone penetration test (CPT), and shear strength test furnish crucial data for refining and validating for soil model use in slope stability analysis. Additionally, risk assessment aid in quantifying the likelihood and consequence of potential failure, allowing engineer to prioritize effective mitigation measures. Such measures may encompass soil reinforcement, drainage enhancement, vegetation control, and structural intervention to bolster slope stability. Through addressing the root cause of instability and mitigation potential trigger, engine can minimize the risk of slope failure and their ramification on people, the economy, and the environment. In conclusion, conducting a true analysis and implementing measures to prevent soil failure and slope instability is absolutely crucial for maintaining the safety and stability of nature man-made slope. To deter such study, utilizing advanced testing technique and implementing effective risk management strategy, we can successfully avoid catastrophic failure and their dire consequence. That's all for me. Thank you.